Hello, and welcome to today's webinar. My name is Naina, and my colleague Arjuna and I are from the AI and Machine Learning team here at AWS. Today, we're going to talk to you about Amazon's Elastic Kubernetes service and the advantages of using the deep learning containers for your machine learning workflows. Over the course of this webinar, you'll learn how to use the AWS Deep Learning Containers, which we abbreviate to the DLCs, to manage your machine learning or ML workflows on Amazon Elastic Kubernetes Service, which we call EKS. You'll also learn how to use training DLCs to run your training workflows on EKS, as well as how to use the Inference DLCs to host your machine learning models on EKS. We'll be covering a few topics today. First off, we're going to cover the concept of using Kubernetes for machine learning. Then we'll dive into the AWS Deep Learning Containers. We'll cover how to train a model on EKS using our training DLCs, and then how to host a model on EKS with our inference DLCs. Finally, we'll point you to some additional tools and resources you can use to learn more about the deep learning containers, EKS, and machine learning at AWS. There are a few topics that it would be helpful for you to be familiar with before you watch this webinar. The first is Docker containers. You should know what a Docker container is and be familiar with concepts like Docker files, Docker images, and Elastic Container Registry. Kubernetes. This tutorial does assume a base understanding of Kubernetes. Kubernetes is a container orchestration system. You should also be familiar with some vocabulary like cluster and kubectl. Training and inference ML workflows. You should also be familiar with high-level ML concepts like training a model and hosting a model for inference. Today, we'll be going through a multi-stage EKS workflow with separate training and inference clusters. We're not going to be covering a unified cluster approach today, or the workflow that would have both training and inference in the same EKS cluster. Finally, we'll be referencing different machine learning frameworks throughout this talk, but a deep understanding of their functionality is not necessary to follow along today. Familiarity with frameworks like TensorFlow, PyTorch, and MXNet will be helpful. There are a few different ways to run your machine learning workflows here at AWS. You can use a comprehensive managed service such as Amazon SageMaker. SageMaker offers a ton of great features and helps you to build, train, and deploy high-quality machine learning models quickly. Alternately, you can take a more do-it-yourself approach using services such as Amazon EKS, ECS, and EC2. This is the approach we'll be taking today. There are a few major advantages to using Kubernetes for your machine learning workflows. Kubernetes is customizable and provides the user more customization options than a typical managed service. Kubernetes is also strongly supported by the open source ML community, so there are a lot of resources and additions available to Kubernetes users. Kubernetes is scalable and offers a variety of features to scale up and down depending on your workload. Finally, Kubernetes itself is not cloud-specific and can be implemented across a variety of platforms and services. To take us into more detail, I'm going to introduce my partner, Arjuna.
Thank you, Naina. Before we jump into EKS and deep learning containers, I want to talk about pizza. Not just because pizza is amazing, but also because we can think of our ML workflows in the same way we think of a pizza delivery pipeline. When a customer makes a request for pizza, there are some things that go on behind the scenes. First, the pizza shop needs to take in raw ingredients and create the pizza itself. Then, the pizza is passed on to a delivery service, which in turn interfaces with the customer and serves them directly. So essentially here, we have two businesses that are involved in getting the pizza to our hungry customer. Note, there might be examples of this where the pizza shop handles both production and delivery of the pizza, but today we're going to focus on the case where two businesses are involved. A potential or typical ML workflow on Kubernetes is a lot like this. Instead of raw ingredients, we'll start with some training data. This data is then processed and trained in the training Kubernetes cluster, generally leveraging a deep learning framework like TensorFlow, PyTorch, or MXNet. Ultimately, this cluster produces a trained model, or pizza in our prior analogy. At the point that we have the trained model, our inference cluster, or delivery service, serves the model and sends predictions back to the customer. So one thing you may notice is that we have these little blue Docker icons in our training clusters. These represent Docker containers. Kubernetes, of course, is a container orchestration platform. Containers include the resolved dependencies and everything that the training or inference job needs in order to run. In our pizza shop example, you can think of the containers like a pizza kitchen, where the pizza kitchen needs to provide all the necessary infrastructure to keep making pizzas. Let's bring back that analogy for a second. Managing a pizza kitchen can get messy and cumbersome. It needs to be cleaned so that customers don't get sick and the restaurant can succeed. A pizza kitchen's appliances also need to perform well to keep up with the scale of demand and serve as many customers as possible. Sometimes the appliances might need to be outright updated. If something new comes along that better suits the business need, we might have to go and get it. Similarly, an ML container can be difficult to maintain. It needs to be clean of security vulnerabilities so that users have trust in the system and data is protected. It also needs to be optimized for performance and scale so that our services can handle whatever comes their way. Additionally, containers might need to be updated when there's a new deep learning framework version or a patch release, etc. Managing a machine learning container can get overwhelming really quickly. You need to manage countless combinations of dependencies like your core Python packages, OS level packages, CUDA and other GPU packages, when maybe all you really care about is packaging your application code with a particular version of some deep learning framework like TensorFlow or PyTorch. Diving in deeper to the systems needed to maintain a machine learning container, you need to write a Docker file in a maintainable location and iterate and build the container. Then you need to write functional, performance, and security tests. After the Docker image is built, you need to ensure that all of these tests pass before you bring them into production. At every step, if there's a failure, you may need to go all the way back to the beginning and rewrite your Docker file entirely. Finally, once those tests have passed, you push your image to a container registry like ECR. While it's there, you want to make sure that you're regularly scanning it for security vulnerabilities so that you know if any critical packages go out of date. Only then, through this pretty arduous process, are you able to confidently use your containers in your application. At this point, you've spent many developer hours and lots of money on compute resources just to get started on your training and inference workflows. Not to mention, your maintenance costs are racking up every time you need to make some changes. To make matters even worse, what if you want to use a new framework version or an entirely new framework altogether? You need to repeat this whole workflow from scratch. All of these steps are work that won't surprise and delight your customers. This is work we do for you for free. Enter deep learning containers. With the DLC, you can get going on EKS right away, and you can confidently stay up and running in production because we maintain the containers with the latest framework, package, and driver versions. Let's dive a little bit deeper into deep learning containers. DLCs provide a set of libraries and packages to train and serve models in TensorFlow, PyTorch, and MXNet across several different platforms like EC2, EKS, ECS, as well as our managed ML service, SageMaker. We integrate AWS optimized framework binaries and packages into these containers. Let's talk a little bit about some of the advantages of using DLC at a high level. So DLCs are equipped with performance-tested framework binaries. They also come with some pretty useful machine learning utility packages. We also provide recent framework versions across TensorFlow, PyTorch, and MXNet. And we regularly release patch upgrades to address new vulnerabilities. We run through a series of security scans prior to each DLC release. The final thing to highlight here is that all our containers are open source. They are free to use, and you can take a deeper look into what's inside and what kind of tests we run by navigating to our public GitHub repo. So let's move further into DLCs. The DLCs come in two major different job types, training and inference. Training DLCs come in several different styles and flavors. We are ultimately going to focus on just one of them, but it's useful to be aware of all of them. Depending on your business needs, you can look through our available images and find the right image for you. We test GPU images, for instance, on a variety of GPU optimized instances, and CPU images on a variety of CPU instance types. So you don't have to worry about performing this testing on your own. Let's double click on the training images for 1 second and zoom in on TensorFlow GPU training images. We'll look into these in action later in this webinar. These images have some useful open source Python packages that you might want to use. We also have some lower level packages like CUDA dependencies, etc. We manage these dependencies for you so that you don't have to worry about them yourself. A more comprehensive bill of materials is available on our public GitHub releases, and you can also inspect the Docker files directly in our public GitHub repo. So we've introduced DLC training images at this point. Let's go ahead and move on to inference containers. Because the job function of an inference service is quite different from a training service, it makes sense that we'd have separate infrastructure for it. Inference containers, for instance, don't necessarily even need our core frameworks. They sometimes just need serving APIs and model serving infrastructure. For inference images, we also support TensorFlow, PyTorch, and MXNet across multiple framework versions and CPU and GPU optimized flavors. We run functional tests across CPU and GPU optimized instance types, and we also have some container images that support different inference hardware. We won't go into that in this webinar. For now, we'll just stick to CPU and GPU. So I want to highlight a couple of things quickly. One is that for MXNet, we bundle in the multi-model server from AWS. For PyTorch in our newer containers, we bundle in TorchServe as our serving infrastructure. And for TensorFlow, we've equipped these containers with TensorFlow serving, or the TensorFlow model server. Let's double click now on the TensorFlow GPU inference images. So you may notice that the bill of materials feels a little bit different for the inference images than the training images. The reason for this harkens back to our pizza analogy once again. This is a totally separate business problem, and thus might require a separate unit of work. Once again, You wouldn't necessarily want a pizza kitchen in your delivery car. You can access the most important packages highlighted in our public GitHub release tags for the inference images. To get the most out of DLCs, it's important to highlight our tagging structure. We apply several different tags to our images, which are all available, once again, in our open source GitHub releases. Here we have one of the more comprehensive tags, so we're going to use it to walk through what each section really means. At the beginning, we define our ECR registry. The nice thing about DLCs is that you can pick the region that's right for you. We are available in 22 regions across the world, and this information is also available in our GitHub repo. The ECR repository name includes some valuable information. First, it includes what framework we're using, and it also includes the job type, which, as we mentioned before, is either training or inference. In our actual tag, we end up referencing the framework version, the processor that we're using, the Python version we're using. In GPU containers, we make sure to reference the CUDA version. And then we also represent the operating system in our tag. We also include a DLC version tag that follows a semantic versioning scheme. This can be useful if you want to stick to a particular configuration, but also get the latest patch updates. Choosing the right tag can be critical depending on your use case. Feel free to navigate to our open source GitHub repo to pick the right tag for you. In some cases, it might make sense to build your training and inference application on top of an existing DLC. This can be a really powerful way of adding customizations on top of your performance-optimized images. In cases like this, it's imperative that you pick the right tag. In this example here, we have picked a tag that pins the DLC major version for this stream. This means that there could be future releases with minor package version updates and backwards compatible changes. However, every time you build a new container, you'll pull in the latest minor version for this version stream. I just want to note that building on top of a DLC means that we ourselves have not thoroughly tested it. So you may need to add some additional testing infrastructure of your own in order to ensure that your additional changes are compatible. Great. So we've introduced some key concepts here like the DLC, inference and training images, as well as dived a little deep into some of the tagging structure. Bringing it back to our early example, we equated the training workflow to a pizza shop. This is where the product actually gets made. In practice, as many of you know, training is often our most intensive step in terms of compute and time. So it's critical that we have the right infrastructure. While it's not usually the interface to our customers like the inference services are, it's still a very key component to our ML workflows. In the upcoming demo, we're going to zoom in on our training EKS workflow. In particular, you might notice that this diagram is a little bit different because we've subbed in DLC as our underlying container. Let's take a look at how this might work. We've spun up a cluster in advance via EKS-CTL and pre-downloaded the kubectl command line tool for this demo. For more information on this setup, please refer to our DLC docs.
In this demonstration today, we will walk you through a quick example of running a training job using our training DLCs. Specifically, we're going to zero in on our TensorFlow GPU optimized training container images. We're assuming some fundamental knowledge of Kubernetes command line tools such as kubectl or kubectl. You might notice that throughout this demonstration, we alias kubectl to just K. Just want to give a heads up there. This demo is not meant to be a step-by-step tutorial. There are some prerequisite steps that we took in order to set things up, such as configuring and actually starting up the cluster. For more detailed and granular information, we've linked some docs at the end of this presentation, so feel free to check that out. For this particular cluster, we use the EKSCTL or EKSCuddle command line tool to spin up a multi-node GPU cluster, which is comprised of P3 8x large instances. We didn't use this exact command, but this is something you might use in order to set that up. All right, let's move on to the actual training job. Today, we're going to train a model using the MNIST database. For those of you who are unfamiliar with this is a commonly used database for testing and training deep learning models. MNIST provides a large array of images of handwritten numbers, and we can use it to train a model to recognize handwritten digits. Let's dive in and open up our YAML file. In this spec file, we define a very basic training job. Let's walk through a couple key advantages of using DLC. The first thing to note is that we're using a TensorFlow training DLC image. This is a GPU optimized image for Pi 3.7 with a CUDA 11.2 stack on Ubuntu 18.04. We're using TF 2.5 for this example. A key point I want to highlight here is the DLC tag that we're using. This DLC tag pins only the DLC major version for this version stream. As we mentioned before, DLC follows a semantic versioning scheme, so we can expect that minor version updates to this particular DLC version stream are backwards compatible with the dependencies in the existing container. The advantage of this tag is that we will pull in the latest patch and security updates for this version stream without having to redefine the image in our spec file ourselves. Note, this might not be the right tag for you, but you can navigate to our GitHub releases to find an appropriate tag for your workflow. The next thing I want to call out is that we're using a training script here to train our MNIST model. Since the DLC comes equipped with a lot of base dependencies, including the framework, in this case TensorFlow, there's little configuration we need to do on our end for this particular job. DLC also comes equipped with utility packages like AWS CLI, so you can push your models directly up to S3 or pull down data sets from an AWS source. Let's go ahead and start the training job. We'll use kubectl to start it up. So at this point, our training YAML is ready to go. We've included our image, which is the TensorFlow training GPU DLC, and we've also included a training script to train on the MNIST dataset. Let's go ahead now and apply the YAML. Note that I will be using kubectl, but in my terminal, I've aliased the kubectl executable to just K. So I'm going to create this new job. And so I've spun up a pod called TensorFlow Training. So let's take a look at the logs. So what we see here is that the training is underway. And at the end of this, we'll have a trained MNIST model. While this completes, let's move on to the next section of our demonstration, which is working with inference DLCs in an EKS setting.
Now that we've trained our model, let's move on to an inference workflow. The next stop on our pipeline is the delivery service. Inference service take a trained model and return inferences or predictions based on what the customer has requested. For instance, if I trained a half plus 2 model and hosted it on an inference service, I'd expect that I could make requests via REST or gRPC API to my server, and I'd send in some number and retrieve a response that was half plus 2 of that number. So that's exactly what we're going to do in this next demonstration. Double-clicking on inference workflows, Let's see what an inference system looks like with DLC.
Let's dive into an example inference workflow now, where we will host a half plus 2 model on EKS using DLC inference containers as our underlying engine. A half plus 2 model should take in a number, divide it by 2, and then add 2 to it. So it should be pretty straightforward for us to validate that this is working correctly. Let's go ahead and take a look at the YAML that will define our service. Okay, so here we are. The first thing I want to point out is the image that we're using. You'll notice that this is different from the image that we use in our training workflow because we're using the TensorFlow Inference DLC. We're actually using the same tag that we noted in our training workflow, but if you want to use a different tag, feel free to head to our GitHub releases and pick the tag that works best for your workflows. The inference containers come equipped with the TensorFlow model server. This is really useful for us because we can use it in order to host our half plus 2 model. We also have nice utility packages baked in, so we can use things like AWS CLI to sync down our trained model from S3 before we serve it. Let's go ahead and set up this service so that we can move towards making requests to our half plus 2 model. Okay, so once again, I'm going to be aliasing kubectl or kubectl to K. So if you notice that I'm just typing K, that stands for kubectl. Let's go for it. All right. So at this point, we've created our service. Let's go ahead and look at the pods to see if it's running. All right, our service is running. Let's take a look at the logs really quickly to make sure everything's working. Okay, we've exposed a REST API port, and so we should be ready to go. So before we go ahead and start making requests to our newly spun up half plus 2 inference service, let's go ahead and set up port forwarding so that we can make requests via our REST API. I'm going to do that now. Great. So let's also take a look at our input data. This is the data that we're going to send to our half plus 2 model, and we're expecting some particular results back. So I've included it in a JSON file. I'm going to open that up. Great. So what we see here is we have a list of 3 numbers, 1, 2, and 5. When we send this to our half plus 2 inference service, what we just expect back is 2.5, 3, and 4.5. This should be pretty straightforward for us to validate. So let's go ahead and make the request. All right, we'll send that in. Awesome, it works as expected. So what we've highlighted here are that the TensorFlow GPU optimized inference containers come equipped with useful packages like AWS CLI to pull down your model from S3. And they also have the TensorFlow model server baked in so that you can use it to actually host your model. Obviously, there were some steps prior to this that we used to set up the cluster, etc. But this should give you a good sense of some of the use cases of using the DLC inference containers in your inference workflows.
Thanks so much for joining me on this journey into exploring some of the benefits of using DLC in an EKS context. I'm going to pass it back now to Nina to wrap things up. Thanks.
Thanks, Arjuna, for that great presentation. To wrap things up, the AWS Deep Learning Containers are a great solution to manage your containers and custom scripts in a Kubernetes environment. Additionally, DLCs can help you to get your training jobs up and running quickly, and using them within the AWS ecosystem can help you to easily maintain and manage a robust system in production. We take care of upgrading to the latest versions of popular frameworks, packages, driver versions, and security updates, and we share our work with the open source community. We've also included the open source DLC GitHub repo, where you can directly inspect the Docker files associated with our DLC releases, as well as take a look at some of the tests that we run. Finally, we've linked an older tech talk by AWS that provides additional context about machine learning on EKS. Thank you all for joining us on this MLOps journey into EKS and the deep learning containers. We hope it was useful for you, and we're grateful for your time. Feel free to keep posting questions, and we'll stay on to try to get them answered. Thanks again.